So hello everyone. So in the previous sessions we had our discussions on naive Bayes and we saw different versions of naive Bayes, and now from today onwards we'll see logistic regression. Okay, so this logistic regression, it again is an algorithm in classical machine learning. So do not get confused with, with this regression term. This basically is a classification algorithm. It's a classification algorithm. Okay, and you have also seen linear regression. So in linear regression that actually was a regression algorithm, but here if you see this logistic regression is a classification algorithm. Just revising the classification, what classification is. So you have been given some data points. Let's suppose you have this xi ith data point, and correspond to this we have yi. So if this yi is given, that we call this as supervised learning. Okay, so this is my data and data comma label. Okay, then its output, this label basically with this yi, if it belongs to some discrete set 0 1 till, let's suppose, k, so we call it a classification problem. Okay, so this xi can belong to some r dimensional vector where each of the value of this vector is r, so there's a real number, and then this yi, this belongs to k. So this basically is, this is supervised learning, and then this is a classification algorithm. So if you see in linear regression, what we try to do is we try to fit a line. Okay, so this was our, if we had some points here, just revising a bit so that everybody is clear with this. So let's suppose these are some points. As you can clearly see that these things are linearly separable, and we have done a mathematical treatment of linear regression that you can see, and we try to fit a best line like this. This basically is a hyperplane. Okay, so what is the equation of the plane? Usually in 2D we write it like this: y is equal to mx plus c. Okay, in general we'll write, we have w naught plus w1 x1 plus w2 x2 and so on plus w dxt, okay, is equal to 0, something like this. So this is the general equation of plane, and then you might, we also wrote it like this: w transpose x, this w naught can be written like this: b plus b is equal to 0. So this is the general equation of a plane. Okay, so this plane, basically if you want to represent any plane, you just have to give me this w and this b. This b is called an intercept. So in the same fashion as we have this y is equal to mx plus c, if you give me the slope and the c, I can uniquely identify a line. In the similar fashion, if you have, now this line is in 2D, if you have 3D 4D 5D and d, so in dimension we call them hyperplane. So hyperplane is represented by this. Okay, just write it here. So w transpose x plus b is equal to 0. This represents a hyperplane. Okay, so by hyperplane we mean that, so this is basically a linear boundary. So there are two hub spaces. There is one called as positive hub space and a negative hub space. Okay, so in linear regression what we try to do is we try to fit a best line. So if you had some points which were like this, so we had some points like this, so we try to fit a line like this so that these errors were minimum. Okay, we also saw least square method. I just wanted to revise. Okay, we try to fit our best line so that if now somebody gives me a point which lies here, let's suppose, and I want to get a value of that, so that value will be, so I'll project it here, and then I'll give this value as the answer. Okay, this was the generic idea of which we saw in the linear regression. So now if you see this, we are going to the logistic regression. Again, we'll somehow have to do with something with the plane. So here also the assumption is that data is linear. So assumption here is that data is linear, or maybe data is linearly separable. I said in every algorithm we take some assumptions. In the naive Bayes we took an assumption that our data, basically in that the features are independent. Okay, in here in this logistic regression we take an assumption that the data is linearly separable. Okay, this also is a statistical method. Okay, so as we saw that logistic regression, that can be, we saw that in linear algebra and how to have a different treatment of that. So here this also was built way before we had these machines, like these powerful machines. Okay, this I think was discovered in like before 1970s. Okay, way before that. So the assumption here, if you see, is data is linearly separable. What's the meaning of linearly separable? So by linearly separable, it means that we can just draw a line or a hyperplane in ND which separates these two types of classes. Okay, so it is used as, it's used for binary classification usually. It's used for binary classification. As you saw that in linear regression, we try to fit this line So here you can get the continuous values. So these were the values which we'll get. Okay, so that's why I here belong to R. That label was basically a real value. That was the thing that we had in linear regression. So this was in linear regression. I'll also come back to this linear regression in detail when we'll see it from the optimization point of view. We have seen this from the point of view of linear algebra. That time we tried to see those null space and the column space and stuff like that. And now we'll see it in different angle in the optimization terms. Okay. So, but if you see this is logistic regression, the same thing is here. Data is also linearly separable here. So there we can just draw a hyperplane which will separate the data, and it is used for binary classification. Is this clear so far?
Yes, sir.
Okay, so if this is clear, then we can move ahead. So I can explain this algorithm in different terms. So this can be explained in terms of probability. Okay, so this algorithm, the logistic regression, I write it LR. So logistic regression can be explained in different ways. It can be explained in terms of probability. It can be explained in terms of geometry. It can be also interpreted in terms of loss function and stuff like that. So we can also use geometry to explain the things, and we can also use loss function. Okay, so now the first part is we'll use geometry to understand this. We'll try to have geometrical intuition, and then we'll again go back to probability, learn some new concepts about probability, because this basically is just an extension of naive Bayes algorithm. Okay, so if you there I'll prove that the naive Bayes and this there simple extension has been done to naive Bayes to come to the logistic regression. Okay, the first thing is we should be really clear about the geometry. How does this algorithm work? And we'll also learn the geometric intuition of naive Bayes there. So if you see the naive Bayes, what we try to do is, so if we had this was a one class and this was the other class, so we try to fit a distribution. Okay, we said project these points on here and project these points on here, and they'll follow some distribution, and here they'll also follow some distribution, and from the distribution see it. And I hope that you saw that we tried to fit the distribution onto one of the features. Okay, that was the geometry of naive Bayes. Okay, and now if you see that this naive Bayes is something called as a generative model. Okay, and this is just a one counterpart. This is called as discriminative model. So this logistic regression is called as discriminative. We'll see the difference between discriminative models and generative models. Okay, they basically we were computing probability of x given y. We are computing this posterior. If we have, let's say, y represents class, so we're saying what is the probability of y given our data point. So this was called as posterior. So if we somehow directly compute this, okay, if we directly compute this, so these models are called as discriminative models. If we directly compute this, so this is just very I'll say basic definition. So because we need to discuss a lot about discriminative models and generative models. So generative model basically what they try to do, the naive Bayes, if you see, so naive Bayes tried to figure out distribution. We saw that we tried to probability of x given y, and then multiply the probability of y. Okay, so this is done in generative models. Okay, there we compute this, and then with this, and then we compute the posterior. And in some models, we'll directly compute this. So that will this intuition we'll see when we will discuss about the probability part, when we'll see the probabilistic interpretation of this logistic regression. But here, the first focus will be we'll see the geometry. Why geometry? Because it's easy to understand, easy to visualize, and then you will have these things in your head. And after that, it will be easy for you to understand the probability also. And for the probability, we'll have to cover some also background for the probability, then we can come to the probabilistic interpretation of this logistic regression. Everybody with me?
Sir.
Okay, so what is this logistic regression? It basically is a classification algorithm that I will write again. It's a classification algorithm. Do not get confused with the term regression. Okay, and then it is used for binary classification. And there are techniques by which you can also use it for multi-class classification and for regression also. So this can also be used for regression, but these techniques we'll see later. But here, if you see, inherently it performs binary classification. It's very simple algorithm, very simple and elegant. It's beautiful. If you see it, like it has very simplicity in it, and then you just need to know the hyperplane and stuff that we have, I think, covered in our linear algebra lectures. So there, if you see it, we'll see it very like simply. There is an algorithm which has a very high simplicity, and then it provides like really great results if you see it that way. Because in machine learning, you don't want a complex model. If your complex model is performing, let's suppose, giving some accuracy, and if there is a simple model which is giving accuracy around that, So it's better to use the simple model. So there are also, you might have seen codes like simple things work very elegantly sometimes. So it's better to like focus on this logistic regression because it's a simplistic algorithm and its mathematical details are not that complex. So it's better to sometimes use it also as a baseline. So we use this algorithm, if it performs better, there is no need to go to the neural networks and use these deep neural networks, stuff like that, because they have a lot of complexity involved. So in terms of computation, we need a lot of resources also. So here, this algorithm is not like that. Okay, now we'll see it's explain these things by the geometry. Okay, so what's the assumption? I wrote the assumption. The assumption here is that the data is linearly separable. So what's linearly separable? We can separate it by some hyperplane, some linear hyperplane. Now we'll see that. So let's suppose we have data like this. Say I have, this is my 2D plane. Okay, let's suppose my data only contains some two features. Let's suppose x1 and x2. This is my x1 and this is my x2 feature. Okay, something like this. And my data is like this. Okay, so this is my data. Now I have to make it linearly separable. So what I'll use blue, these circles. This is my data. As you can clearly see that in 2D, we have two features for x1 and x2, and this is clearly linearly separable. Let's make one crossover here for the misclassification. This is nearly separable. This is not perfectly linearly separable, but this is nearly separable. Okay, something like this. Okay, so let's suppose I'll call this as positive class and I'll call this as negative class. Let's call this blue as negative class. This is my positive class. So this is my setting like something like this. Okay, so if you clearly see that, if you see geometrically, so everybody of you will say me draw a line like this. Okay, so I'll draw a line like this. So whatever is on this side, okay, this is a positive class, and whatever is on this side is a negative class. So this is just, we can see it by geometry. Okay, now we just need to extend it. We just need to see it how mathematically how can we put it mathematically, because many times we understand the visualization, then we have to make it mathematical. We have to do the mathematical treatment of this. Okay, this is very elegant if you see it. So if some data looks like this, so you can just separate it. So if you remember the again, I just revised linear regression. In that, what we were doing is we had basically data such that we fit the line. Here we don't fit the line like this. We just draw a line which separates the data. Okay, the data is like this and is linearly separable. So we want a plane like this. So plane, usually this hyperplane is, and this is denoted by pi. So it has these two, it has this feature of w. So w is a vector because we saw that w transpose x plus b, this is the representation of hyperplane. This b is basically an intercept, and this is called as weight vector. This w is called a weight vector. So this pi has two properties. This is weight w and b. This is weight and this is bias. Okay, so if you forgot, if you have forgotten these details, just go to the algebra lectures. You'll see why do we basically show this hyperplane by w and b, two parameters. So I just need to find this w and b. I'll find the whole parameter. I'll find the whole hyperplane. Okay, so this is my hyperplane. I'll write it here. Okay, so here the data is clearly linearly separable. Now my job is to find such a w which separates the data like this. This is my job. The whole point is that I have to find a plane like this. So how to find a plane? In plane I have to find w and b. That's my job. I have to find w and b such that when I find this, so for that w, when if I give these input, these are my axes, so they will be linearly separable. So now let's see what is so good about these things. Okay, what is so good about this hyperplane? So let's suppose I have a point right here. So if I take a point, this point, so what's the distance of this point? Okay, let's suppose this is just point I. So what is that? What is di over here? In also in algebra we saw that this di distance is basically w transpose xi plus b divided by norm of w, if I'm correct. Okay, so this is the distance of this. So if you have to compute distance, so you can just use this formula, and we have also derived this formula in our lectures of linear algebra. That's why I said linear algebra is really important. Okay, so here we have this w. So this is my w. Okay, this is w vector, and now this is di. So di here is w transpose xi plus b and divided by mod of w. So if we assume that this w is a unit vector, this w is a unit vector, and we say that b is equal to 0, that means the plane passes through the origin. We can make it. Okay, we can make it like this. There is something called affine transformation. Okay, we can make this transformation so that we make this di equal to w transpose xi. So I can also write this di like this. Okay, if this is if this w transpose, what I'm saying is this b is equal to 0, that is it passes to the origin, and then this w is equal to 1, it's a unit vector. Okay, so I can write this di like this. Okay, now if you see that, if you see this diagram, If you see this diagram, if this W and this DI, if they lie on the same side, so if they lie on the same side of the plane, so this point lies on this, and this W has a direction like this. So you know from the dot product, this W transpose Xi will be greater than 0. Okay, because this is just a dot product. Okay, and if they both lie on the same side, so this will be greater than 0. So this side will be greater than 0. That means for positive class, W transpose Xi will be greater than 0. That is distance of the point from the plane, from the hyperplane. This will be positive. Okay, and W transpose Xi, if this is less than 0, that means the class is negative. That means W is from here and this is on the opposite side of W. Okay, that means that these points basically they are on the other half side. This is called as positive half space. This is called as negative half space. Okay, this is positive half space and negative half space. So you can clearly see that this is our distance. So if we have point I, so Di, its distance is, let's take this is point J, some point J, Dj. If W transpose Xj is less than 0, then it's a negative class. So who understood this so far?
Yes, sir, got it.
Okay, so what I'm saying is, so if you have a point which is lying in the positive half space, that means this distance will be positive. Okay, and otherwise the distance will be negative if it lies in the negative half space. Why is that so? Because we compute the distance using this formulation W transpose Xi, and if these two vectors lie on the same side, so the angle between them, if you see, because this is just a dot product, so cos theta will give you the positive value. Okay, so if they lie on the opposite side, that basically means this is less than 0 and it will give you a negative value. Okay, this is like the starting of the linear regression. We are trying to understand this logistic. We are trying to understand the logistic regression. So we saw if we somehow found this plane. Okay, now there's a beautiful property. The property is that whatever points lie on the positive half space, so for these points, the distance is positive, and whatever points lie on the negative half space, the distance for these points is negative. Everybody should be clear on this point. If you are clear, then only I can move ahead. Are you clear with this?
Yes, sir.
So if you are clear with this point, then I can move ahead. Now, what should we do? The point here is, let's call this, let's use some notations. So we'll say this as +1, and we'll say this as -1. Sometimes we use 1 0. Here we'll use +1 and -1 because for the mathematical ease, so that we can easily formulate this math as a mathematical problem. Now you know that if you see this W transpose Xi is greater than 0, so for that it's positive. So that basically means Yi is +1. Okay, and now for this Yj is -1. That's how we defined the problem. So in the problem, what we did is, so we said we'll call positive points as +1 and we'll call negative points as -1. So this is my positive point. So this is my positive points, and these are my negative points. Okay, so ideally what should happen is, so whenever a point is on the positive half space, so for that point W transpose Xi should be greater than 0, and then W transpose Xj is less than 0 if it is on the negative half space. Then what I have included, I have said that I will call this positive points, for them label is +1, and for the negative points label is -1. I won't say 1 and 0. So maybe we'll also use 1 and 0 when we go to the probabilistic interpretation of this. But here, just understand that we are here representing positive by +1 and negative class by -1. So that's how we see it. So if there is a point which is positive, that should get labeled +1, and for negative point, label should be -1. And this is the property that we saw. Okay. Now we see that there is a beautiful thing. Let's suppose a point is positive. If a point is positive, if a point is actually positive. Okay, and we are trying to find the hyperplane. So there can be two cases. Either it can be a misclassification. It can be a misclassification. Okay, or it can be correctly classified. Correct classification. Please focus for roughly for 4-5 minutes so you understand this. So in the misclassification, actually a point is positive. So Yi, actual Yi basically was +1, but predicted Yi, this Yi hat, this is called a prediction, what the prediction would be, and this was -1. So here it will be misclassification. Correct classification means Yi actually was positive, and but prediction given was also positive. This is correct classification. Everybody with me on this point? So this is the misclassification, and this is the correct classification for a positive point. A point is positive. Now I told you that. So when will there be a misclassification? So actually what happened is W transpose X. Okay, this should have been greater than 0, but our algorithm would have predicted this to be less than 0. Okay, because actually in actuality this should have been W transpose X should have been greater than 0, but when we made a prediction, this Yi hat, it would have been less than 0. Okay, am I clear? Am I clear with
Yes,
this?
sir.
Okay, so if you see, this has been actually given as less than 0. Now if you multiply with this, let's suppose we say we'll take this. So our algorithm predicted this as less than 0. Now if you multiply this actual label, so yi transpose w transpose x, so this basically was plus 1, so this will again be less than 0. Okay, do you understand this? If you understand this thing, so how many of you understood this?
Yes, sir. Got it.
Because actually this was our actual prediction, this is our prediction. Okay, but in actuality this should have been a positive point. It should have predicted w transpose x is greater than 0. This should have been the correct prediction, but it actually misclassified it. That's our case first, it misclassified. So we had w transpose x is less than 0. So now you have multiplied with the actual prediction, you will see that this still remains less than 0. Okay, now we'll go to the correct classification. So correct classification, this w transpose x is greater than 0 should be true. Actually when we performed the classification, it did that. That means w transpose x is greater than 0 was predicted. Actually this is also predicted. Now if you multiply it by yi also, this yi w transpose x is greater than 0. Can I write it like this? How many of you agree on this?
Yes, sir.
I just multiplied y on the both sides, because now you see that yi was positive, so it won't change the sign. So this is the first, this is for positive points. So now let's do the same treatment for the negative point, and we'll see a pattern there. Okay, let's suppose if we have a negative point. Now if we have a negative point, so what is possible there? Basically yi, so label here is -1. This is my label. Now here can be misclassification, or it can be correct classification. It can be correct classification. Okay, so what's the meaning of misclassification? So misclassification will say this yi predicted, this basically is +1. This will be the prediction. The actual label yi was actually -1. So here yi is equal to -1, and prediction also was -1. I hope that you understand this. This is my prediction and this is my actual label. Okay, now if the misclassification happened, w transpose x should have been given less than 0 in ideal case, because this was a negative point. Now our prediction was w transpose x is greater than 0. This is what we predicted. Okay, this is what we predicted. So this quantity was basically now greater than 0. Now if I multiply this, so if I multiply this with actual yi, so if you see, if I multiply this with actual yi, so what will happen is, so this will become yi w transpose xi is less than 0. How many of you understood this? If I multiply with actual yi, because this was a positive quantity, positive multiplied with negative, it will become a negative quantity. This is a positive quantity. When I multiply it by -1, so this will become whole negative quantity. So how many of you understood this?
Yes, sir.
Same for this. So now actual should have been w transpose xi less than should have been predicted as 0. Now it's correct classification. That is, this would happen actually. So now if you see this w transpose xi and multiply it with the actual label yi, so this still will be 0. Okay, now if you see that this is greater than 0. Why is this greater than 0? Because now we have this yi was negative and this was also negative. So this quantity was negative and this yi was negative. Negative and negative multiplied gives us a positive quantity. So how many of you agreed on this? So in the first, if you see this misclassification, this is the thing that holds, and in the correct classification, this is the thing that holds. And again in the same, if you see, if a point is positive, this is the thing that holds, and if point is positive and it's a correct classification, this point holds. So now seeing these four equations, what I can say is, if yi w transpose x I is greater than 0, then it's correct classification. Okay, and if yi w transpose xi is less than 0, it is misclassification. How many of you agree with me on this point? So if you guys agree on this point, then we can move ahead. Do you agree on this point?
Yes, sir.
Zakir?
Yes, sir.
Let's go back again. I'll just revise it like we have two cases. So a point can be positive or a point can be negative. Okay, there can be positive point, there can be negative point. So for positive, we said the class label yi will be actually +1. Okay, now there can be two cases. So what algorithm we are using? So right now we are discussing about logistic regression. So the point there is, so we should have actually predicted this w transpose x is greater than 0. So this should be the prediction. This should be actual prediction. But our algorithm will misclassify. In the misclassification, this is what that algorithm would have predicted. W transpose X is less than 0 because it was misprediction. Okay. Now if you see the actual label yi, it was +1. So if you, this is our negative quantity, and then we have the positive quantity. If you multiply positive quantity and negative quantity, it will be negative quantity. That's what I wrote here. Yi W transpose X is less than 0. So for misprediction, you saw that this equation holds. Okay, again we'll go to the misclassification in the negative class also. So for the negative class, if you see, yi was -1. Okay, so actual prediction should have been W transpose Xi is less than 0. But what our prediction would be, this will be our actual, this will be prediction, because it misclassified it. Okay, so this should be the actual thing, but this is the prediction because it's misclassified. Now if you see that this yi is negative, so we have a positive quantity that was predicted, multiply with a negative quantity, positive multiply with negative is negative again. So if you see in both misclassification, yi W transpose Xi is less than 0. Okay, so yi W transpose X is less than 0 here, in positive class also, in negative class the same. But if you see the correct class classification, in the correct class, first the positive classification in positive class when it was correctly classified. So what we predicted, actually the prediction should have been W transpose X is greater than 0. That is what was predicted, and if you multiply it with a positive class, you will still get a positive result. Okay, Wi, because this is positive and this term is also positive. Positive multiplied by positive is positive. That's why I wrote it. W transpose Xi, this basically is greater than 0. For the same for negative class. So now this term was negative. So W transpose Xi was negative. So now we also had this label as negative. That's why I said we'll use it at +1 and -1 because it eased out our formulation. So now yi W transpose Xi is greater than 0 because this is negative and this is also negative. So negative multiplied by negative, this gives us a positive quantity. That's what I wrote is. So if yi W transpose Xi is greater than 0, it is correct classification. If yi W transpose Xi is less than 0, it's a misclassification. Basically the point was misclassified. So how many of you understood this?
Yes, sir. Got it.
Okay, so now we'll see what that basically means. So in this picture, if you see it over here, okay, so for these points, okay, they will be they'll be classified correctly because they have positive distance, okay, and they have positive label also. So positive distance multiplied by positive label gives us positive. So all of these red points will be correctly classified. But for this point, it will be a misclassification. Why? Because Wi transpose X will be greater than 0, but its label is -1. So it will be a negative quantity. So this Wi transpose yi W transpose Xi, this will be less than 0. Now why? Because this distance was positive. Distance is this much is the distance, and this yi is the actual label. So this was equal to 0 because this distance was positive, yi was negative. So when you multiply these two things together, it will be less than 0. So this will be misclassified. So you also understood what the misclassification, how will be the misclassification seen geometrically. So geometrically, so basically it should have been predicted this as a negative class, but it predicts it as positive class. So geometrically, this is a misclassification, and this also is a misclassification. Why? Because if you see distance over here, this is negative, but its label is positive. Negative multiplied by positive is negative. So for negative, this is a misclassification. Everybody with me?
Yes, sir.
Okay, so the thing is, we somehow have to do this. We somehow have to get the classifications correctly. Okay, that's our problem now. So because this is misclassification and this is the correct classification. Now what I want to do is, I want my data points to be correctly classified. Okay, I want at least my most data points should be correctly classified. That means I have to find such a W, okay, which maximizes this, which makes it positive. Okay, so what was the problem? I have to maximize this yi W transpose Xi. Why I have to maximize it? Because I want it as positive as possible. Okay, let's suppose for all the points. Let's suppose for all the points now. For all the points, I goes from 1 to n. Let's suppose I have n points. For all the points, I want this to be as positive as possible. Okay, I want to maximize this. I want to maximize this because I told you that for all this it should be positive. So when you add positive quantities together, you will get a positive quantity. Now the thing is, for all the points, if I get it as positive, so then sum will become maximum. The reason that the thing is that I want to maximize this sum. Okay, and but the point is, I want to maximize because I can only, this is fixed for me. This data is fixed for me. These two things are fixed for me. I can just change this. So the problem is that I want to find such a W which will maximize this quantity. How do we write that? We write that like this: arg max of W summation of I is equal to 1 to n yi W transpose Xi. So what is the meaning of this? The meaning of this is, I want to find such a W which maximizes this value. Okay, this is for all the points. Okay, so this we call as W star. So I want to find such a W star. What is W star? Oh, sorry. So W star basically is I want to find a hyperplane because B is equal to 0. And you can also say I have to find B also. But I have made in transformation that this plane passes to the origin so that B is equal to 0. Now only thing that we have to find is this W. So I want to find such a W for which this thing become maximized. Okay, and that's why I write argmax of W. That means find such a W which maximizes this equation. So if you again remember naive, so there we wrote argmax of yi. We want to find such a class for which probability of yi given x is maximized. Okay, I want to find this I want to find such a class for which this probability maximized. So if you see this, the problem over here is I want to find such a W for which this thing is maximized. Why? Because we have given the problem in such a way. Now the assumption here is that positive class is +1 and negative class is -1. Okay, and distance di that we have, that is measured by W transpose xi. This is the distance di. Okay, and B is equal to 0. And now our data is also linearly separable. How many of you understood this equation?
Yes, sir.
You understood this equation?
Yes, sir.
Okay, now our data point is fixed. The point is this xi is fixed, this yi is fixed. The only thing that we can change is this W transpose. My job is to find such a W, okay, such that this is maximized. Now again going to geometric interpretation. Okay, I'll go to geometric interpretation back. Okay, then my points were like this. These were my red points, positive class. Okay, and then I had blue circles which were my negative class, something like this. Okay, so let's suppose I make a plane like this. If I make a plane like this, so maybe I should make points countable. Okay, let's make only 4 5 points so that I can count them. This is 1 2 3 4 and 5. Okay, I'll also make this crosses as 5 points only, maybe 4 or 5 points. 1 2 3 4 and 5. Okay, so let's suppose this is my data, and now you can clearly see this linearly separable. Let's suppose I make a plane like this. Okay, let's suppose I'll call this pi1. This is my plane 1. So for this, if you see, let's make this point over here. Let's make over here. So the points that lie on here, so okay, they'll be called as positive points, and the points that lie here are called negative points. Let's assume, for the sake of simplicity, each of this is distance d1. Okay, this is d1, this is also d1, this is also d1. Simplicity. For the sake of simplicity, I'll tell this. So what you see over here is, let's suppose for this point, and they are correctly classified. This point is correctly classified. So what is the sum then? So if you see, this point is correctly classified, this point is correctly classified. Okay, because these are positive points, and then these points are negative points. They're also correctly classified. But there are 3 misclassifications if you see. Okay, so this is pi1. So pi1, if you see, it makes 3 misclassifications. Okay, do you agree with me on this? Why does it make this? Because this is our d1 and this is misclassified. This is misclassified, this point. So point over here, this point basically. These 3 points, this and this are misclassified because they are in negative half space. So we have 3 misclassifications. That is, if you see this equation. So if you put it over here, if you put this, because we want to maximize the value. What is the value over here? So for this +1, +1, +1, +1, +1, +1, +1. Let's suppose for these 3 it will be -1. Okay, so we'll have +2 and -3 and +1, 2, 3, 4 and 5 +5. So how much is the value of this? So this is 5, 7. This is 4. I think +4. So what I'm writing is, I'm basically writing the summation of yi W transpose xi. So what's the value of this? I should maximize this. So I'm saying for pi1, this value is equal to +4. Is it clear? How this value is equal for pi1, how this value is +4?
Yes, sir.
Because we are assuming that distance for each of the points is 1. So if you see 1 + 1, because they are classified as positive points, so it will be like this. So this W transpose xi is greater than, this is equal to 1. So this distance is equal to 1. So this distance is equal to 1. Now they are also positive labels. So multiplied by 1. Okay, so this will be equal to 1. Okay, so for this point is 1, for this point it's 1. For these points is again 1. Why? Because W transpose xi is less than 0. It's -1 for these points. That's why I have computed distance. I said they are from distance 1 apart. So then when you multiply it by -1, this will again become +1. So for these it's again +1. For these it's a misclassification. Now it will be -1 for these. So we have +2 for these 2 points, we have -3 for these 3, and we have +5 for these 3. And then if you sum up by using this equation, if you sum up, just wait, let me adjust it. So if you sum up by using this equation, you can clearly see that for all the points, if you sum it up, we will get yi, you'll basically get this yi w transpose xi. So for out of how many points, we have total 10 points. So 2 points we get positive, we get plus 2, then we get minus 3 because this is a misclassification, then we get plus 5. So this is 4. Okay, so this is for pi 1 when you make this plane, this pi. So this is the plane pi 1. So now I'll make some other plane. Just removing these. Okay, so here I have 2 more points. Okay, now I will make a plane like this. So this is my 1, 2, 3, 4 and 5 points. Now if I make a plane like this, now visually you can also see, let's call this plane as pi 3, pi 2. Okay, for pi 2, so this will be correct classified, all of these points will be correct classified, so all points basically will be correctly classified. So if you now ask me what is this, so if you compute this, so this will be equal to actually 10. Okay, so the maximum value that you can get out here is plus 10. Okay, and that is by this pi 2. Okay, if you saw pi 1, so what pi 1 gave us? Pi 1 gave us 3 misclassifications. Basically there we got the value of 4. Now if you see it over here, so this will be w transpose x, I will be 1 for this same 1, 1, 1, 1. Again for this it will be minus 1, minus 1, minus 1, minus 1, minus 1. But when you multiply them with the label, you will get plus 1 for everything. So the value for pi 2, this equation's value becomes plus 10. So which is better? Is pi 1 better or pi 2 better? So which plane is better? Zakir, which plane is better?
Pi 2.
Why is pi 2 better? Because the whole point is to maximize this. Okay, geometrically you can also see that this is the pi that maximizes it. That's what I say, that you have to find such a w. You have to find such a w. You have to find such a plane. By w I mean you have to find a plane. You have to find such a plane for which this value is maximized. I hope that you understood this point. So why do we want to maximize this? So the equation that I am currently in here is arg max of w, because you take summation over all the points from 1 to n, yi w transpose xi. So this should be maximized. Okay, so we call this as optimal w, optimal hyperplane. This is what we want to find. Everybody with me so far?
Yes, sir.
Okay, so who else is in the class? Let me pause for a while. Now we are convinced that we want to maximize this equation and we want to find such a plane for which we can get maximum value of this. Now you see that I'll show you some problems with this equation. So there are problems. Now we had to adjust it. So the first problem is that this is prone to outliers. This is prone to outliers. So what is meaning of the outlier? Outlier is which is out of the norm that we have seen, and then we have to modify this equation so that our equation, whatever we want to maximize, that should not be outlier sensitive. Okay. So whenever we have outliers, so there will be some problem. So let's just have a case like this. So let's suppose I have these points like this. Okay, and these are 1, 2, 3, 4, 5, 6, and now I have a point like this. I have some circles like this. Okay, this is 6. I'll draw a plane like this. Okay, now I'll have a point over here, somewhere over here. Let's suppose some point is over here. So this is an outlier. Okay, let's suppose for all of these distance is 1. For all of these distance is 1, 1, 1. Okay, for all of these points, and for this point let's suppose distance is 100, or maybe 200. We'll call 200 is a good number. So because now this it's an outlier, you saw that all these points have distance of 1, 1 from this pi. Let's call this pi 1. Now we'll see the summation of I equal to 1 to n yi w transpose xi. So what's the value of this? Because we want to get a maximum value of this. So now if you see this, for this it will be plus 1. So plus 1 plus 1 because this is positive class and this is our negative class. Negative class. So now you see this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we'll get plus 12. But for this point, the distance is 200. Okay, then we'll get minus 200. Why? Because it's misclassified. By this hyperplane, this point is misclassified. It should have been classified as a positive point, but it is misclassified. Now you see that this basically is equal to 200 minus 12 is 188. Okay, I think 188. So this is minus 188. Okay, now this is the value for this, because now we want to maximize. This is our pi 2. Now let's construct pi 1. Okay, we'll make another, this is pi 1. Okay, for pi 1, this is our pi 1. So we'll construct another have a plane, we'll call it pi 2. So if I have pi 2 like this, let's suppose I have pi 2 which is somewhat like this. Okay, this is pi 2, this is my pi 2. So for pi 2, if you see that this point is correctly classified now because it's on the negative half space. Okay, so this is positive half space. So this is plus 200. Okay, then these points are also classified as correctly because this is negative half space. So these points 1, 2, 3, 4, 5, 6 plus 6, but minus, and how much is this? Minus 6. So this is plus 200 value. So now from our algorithm, from this W transpose xi, yi W transpose xi, you have to maximize this. It seems that pi 2 is better. How many of you see that? From the equation it looks that pi 2 is better because we want to maximize this value. For pi 2 we got this 200, but for pi 1 we got minus 188. But if you see visually, there looks something is bad here. This pi 1 should not be there. This pi 2 should not be better than pi 1 because pi 1 correctly classifies 1, 2, 3, 4, 5, 6 points. But if you here see that there is an outlier when we compute this distance. Okay, this distance was 200 and it was giving value plus 200 for this hyperplane pi 2. But for pi 1 it was giving the value of minus 188 because one outlier was misclassified. So what do you want to do is you want to somehow this pi 1 should be the answer. So how many of you see this problem? How many of you are able to see this problem? The problem here is that if you see this pi 1, visually it looks like this is a good classifier than this because we had just one outlier. But mathematically if you use this, so this equation we have to get the maximum value. For pi 1 we are getting the value of minus 188. Okay, why? Because there is an outlier and it has very high distance, the d is very high. Okay, and then if you see this pi 2 is plus 200 because it's just misclassifying all of these positive points are misclassified. But this outlier is correctly classified, and now you see that it is showing the value of plus 200. So if you just want to maximize this equation, the problem is that this is outlier sensitive. When there will be outlier, there will be a problem. So if there is an outlier, so outlier will basically give us that pi 2 which is not optimal. This is called as suboptimal. Okay, so we'll get suboptimal answers if we have outlier, if we just maximize this equation. Now you see the problem. So we were trying to argmax of W for Wi W transpose xi, and we try to maximize this for all the points. Now you see this, we have a problem with this, that it is sensitive to outliers. If there is an outlier, then the whole thing falls down. So that I showed by the example. Now we have to somehow modify this. Now the question that we faced is, it is sensitive to outliers. It is sensitive to outliers. Okay, so now my job is, okay, how to make this such that the algorithm does not get affected by the outlier. How to do something with this. Okay, the point is I have to change this somehow. Okay, and this y will remain fixed. Okay, I have to change, even I can change the whole or something. I can transfer it through a function or something. So if you see this, all of these were d1, d1, d1. So can I have a threshold? Can I have a threshold such that if the points are till certain distance, I'll have this distance sort of increase linearly. But if there is a way more distance, I'll have a tapering off behavior. What is that tapering off? Let's say for this 200, I'll not write 200. I'll write 5 or I'll write 3. Okay, I should come up with a function such that, so now the question is this, our algorithm is sensitive to outliers. Now what is the answer? Now you know that why is this behavior? This behavior is because this distance is very high and we are including this 200. So this 200 we are including in our distance. Now what I am saying is, I am saying that instead of this value directly taking this value, what I can do is I can transform this value. I can transform this value such that for some value, let's suppose if you have values till some 2 or 3 distances there, it will give some values accordingly. But for the higher value, let's suppose we got value of 2000, it should give some value around 3 or 4 or something. It should give the value in that range so that outliers won't affect it. Because you saw the problem. The problem came because of this distance. Now I want to transfer, I want to have a function when I give this as input. So that what should that function do is that should transform this. Okay, how should that get transformed? The point is that for larger distances it should taper off. That means it should have some behavior like this. Let's suppose for small values it should grow linearly. Okay, for something it should grow linear like this. Okay, then if the values become higher, it should taper off. Okay, that's what I mean by tapering off. So this is called as tapering off. We should have a squashing effect. We call it also squashing. We squash the values, okay, because when we have very high values, that's the problem where we have these values from. So if you see, that's how a mathematician thinks. Now the math, that's a problem. If mathematician was faced by this problem, he sees, oh, I see a problem here. So problem is because of the distance. If I can come up with something, some transformation, so that if there are small values, so they linearly increase, the distance will linearly increase. But once this distance gets way bigger, so I'll taper off this value. So I'll not consider 200, I'll maybe consider 5, 4, or something like that. So this is the behavior I want from the function. So it should first increase till a point, and then it should taper off. And similarly for here, for these values, okay, some behavior like this. Okay, so do you understand why is this? Do you understand why do we want to perform this squashing, or why do we transform? So how many of you understood this? Why do we want to perform this transformation, or what's called as squashing? Amir?
Yes, sir. Go on. Yes, sir.
The problem that we're faced with, because we had outliers which had very high distance of 200, and that gave us a problem. So because when we directly use this equation, that time we had a problem that this 200 had more weight. Now what we want to do is, we want to linearly assign. Let's suppose for 2, 3 values will compute distance. Once the distance gets very high, so what we want to transform is, let's suppose the distance is 500. Okay, I want to give this 500 a value 5, not more than that. So this value should be 5. This value should be given 5. So now I need to come up with such a function. So what I will do is, I'll come up with a function f, which given this value, this yi w transpose xi. So what will it do is summation basically. So I'll give it value. I'll make a function f, which given value of the summation of I from n yi w transpose xi. When given this value, it should show me this behavior. Okay, so what should it do is, for larger values, it should taper off. Okay, it should make this constant, some smoothness in the curve if you see that. Okay, so one of such function is called as sigmoid function. Okay, sigmoid function has such a characteristics. So what's the characteristics? It tapers out a certain value. So the sigmoid function is something like this. So f of x is equal to 1 divided by 1 plus e to the power minus x. This is called as sigmoid function. Okay, it's represented by sigma sometimes. Okay, this is called sigmoid. It has exactly this behavior. Okay, so if I want you to see this, so I'll show you a function which shows exactly this behavior, the sigmoid function, and I will draw this, because I have also shown you a calculator which is called as Desmos. Okay, let us go to that calculator and let me show you. I hope that my screen is visible. Now if I write this, y is equal to 1 divided by 1 plus e to the power x, e to the power minus x. Okay, minus x. So you see this function. So for this values, so first it's initially linearly, if you see it over here.
Screen is not visible.
So if you see it over here, so now I wrote this function y is equal to 1 divided by, this is the function that I wrote in Desmos calculator. So now what you can do is, you can see this function. So from 0 to like nearly till 2. So this value is sort of going linearly, and then it is tapering off. So this is the tapering off effect. This is quotient. And similarly for this, again it's linearly increasing, and here if you see from here, this is linear increase, or we can say linear decrease on the other side, and then it tapers off. This is a sigmoid function. This is our sigmoid function. Okay, this is the function which we will use so that our the thing that we have, the function that we have, we want to taper off its effect. Okay, I think this is clear to all of you. So what I want is, I wanted tapering off. So I said I'll pass all of these values. I'll pass these values through a function. So I'll pass these values through a function. So what is the function? Basically, I can take this value. So I can take summation out, because I'll take this value for individual values. The summation should not be inside. Summation should be outside. Okay, I'll use this function for all of these. So what is the equation now? So the equation becomes y divided by 1 divided by 1 plus e to the power, okay, what is that? W transpose xi, what negative of this. Okay, and now we want to maximize this. Summation of I is equal to 1 to n, because now we want to maximize this thing. Everybody with me? So let's call this I can write it sigma. I can write it like this: sigma of minus W transpose xi. Okay, so this whole thing I wrote it as sigma, and I'll sum it over xi to the power I to n. Okay, now what is this equation now? This equation, if you see it, it's a beautiful thing. Why? Because it shows the tapering of behavior. Okay, now I want to find such a W so that when I have the higher values also, so it somehow tapers off that effect. It does not, it is not sensitive to the outliers now. I hope this is clear. Is it clear? Or should I again
Yes, sir.
explain this?
No, sir.
So what's the function that did it? So sigmoid function did it. Okay. Now I want to find this. I can write argmax. So argmax, I want to find such a w, which is w star, for which this gets maximized. For which, oh, sorry for this. Okay, I have to run through this again. Yes. So what I want here is, so now I want to get argmax of this. So the equation is, so basically we wanted to maximize yi w transpose xi for all the points we wanted to maximize this. But we saw that this, there was a problem with this. So we want basically argmax of this. Argmax of this. I want to find such a w for which this equation gets maximized. Now you saw that this was sensitive to outliers. To outliers. Okay. Now after that, what we saw is, we said what we'll do is we'll pass this through this distance. We'll pass this through sigmoid function. So we'll write that sigmoid with sigma now. So we'll pass the sigma yi w transpose xi. Okay. Then we'll take sum over all the values. Sum over all the values. I goes from 1 to n, and now we'll take argmax. Just give me a second. I'll stop the recording also.